Okay, let's start our session. The screen is visible, right? Yeah. Okay. Okay. Good morning, everyone. Today, some of the sequential circuits like sequence detector and counters. This is the plan for today. As I told you earlier, we are going to build a sequence detector and simulate it in logism. After that, we will be seeing the excitation table for T flip-flops. And lastly, we are going to like discuss and simulate different types of counters in logism evolution. So moving ahead. Okay. Um, okay. Uh, okay, we are going to build a sequence detector in this session. It, we're going to build a sequence detector which detects the sequence of 101 in our continuous array of inputs we will providing. Let's say we are giving the inputs as some random thing. Our output, like our sequential circuit, should detect whenever the last three digits correspond to 101. See, I have underlined the digit where the last three digits correspond to 101. Correspondingly, I have written the output as 1. See, and rest of the cases, the output given by the sequential circuit should be 0. Let's see each and every underline digit. See the last three digits. It's 101. See here. It's also last three digits are 101. Okay. Wherever I underline this, the last three digits are 101. So our circuit should detect the sequence of 101 by giving an output 1. Before going to the building part of the circuit, we need to discuss about state diagrams. Okay, what's a state diagram? State diagram is an pictorial representation of our how our sequential circuit should work. Like in programming, we have a concept of flow diagram, right? Similar to that, it's an electronic counterpart. We are first going to build the state diagram. Okay, in which each states are represented by a circle. Uh, I will tell you what exactly are we doing, like the states and all. This is the state diagram we are going to discuss now. Okay. Uh, okay. This is the same state diagram I have taken from the presentation. Okay. What are we first going to do? Uh, like our circuit needs to detect a sequence of 101, right? But we can't directly, like our circuit can't have the ability to directly detect the sequence of 101. So I'm going to break it into like 4 levels or 4 states. Like the first state is nothing special, does not have anything. The state 1 is where it detects 1. State 2 is where our circuit detects the sequence like 0 after 1. So I put 1 0. State 3 is the state where our circuit successfully detected the sequence 101. So I am dividing our complex sequence in such a way that it will be simple for the circuit to understand it. So this is why I separated them into 4 different states, starting from S0, S1, S2, and S3. As you guys can clearly see, uh, from S1, if I in the state diagram, I put many arrows, right? The numbers which are in the arrows are nothing but the corresponding values of corresponding input values. See that S0, when we give 1, it goes to S2. After going to S2, again, if we give the input value as 0, it goes to, after going to S1, if we give an input value of 0, it goes to S2. After reaching S2, again we will be giving 1. It will be reaching S3. This is the our sequence path or our correct path. See, our sequence is there, right? Like see 1. 0, 1. It exactly matches with the sequence we need to detect. So we have successfully broken the complex sequence into 4 separate states, or you can say it as a level, however you want. Okay, now we know like from S0, if we give 1, it goes to S1. But there are cases where we will make some, like the sequence will break, or we will give wrong input so that the sequence completely breaks, right? So I'm going to discuss the cases now. Okay. In case like we will start from S0. In case S0, there are two possibilities, right? One input can be 1, other input can be 0. First of all, go and check. Uh, sorry. First of all, go and check whether there is an state corresponding to the value 1. Yes, that see that see in this. Yes, there is a state corresponding to the value S1. So I'm putting like from S0, if I give a value of 1, it goes to the state S1. See this line. And in case where if we give an input of 0, in this case, 0 means there is no state, right? If we find no state at all, we will go back to the beginning state, which is beginning state, or you can call it as reset state as you wish. S0. So from S0, if I give an input value of 0, it will go back to S0 itself. Okay, now we will discuss about the all possible cases of S1. Okay, let's say we have successfully reached S1. After reaching S1, there are two paths. One is we will get 0 as an input, other we will get 1 as an input. I'm going and check whether going and check whether we have a value for like state for the number 10. Yes, there is a state for the number 10, S2. So it goes to S2. So S1, whenever we will give input value 0, it goes to the state S2. Okay. Again, there is another possibility where our input can be 1, right? In that case, our number will become 1, 1. See, there is no 2-digit state corresponding to the number 1, 1. We only have a state for 1, 0. So I'm going to drop this value of 1 and consider only this value of 1. So I return this value of 1, the last rightmost value, and I'm going and checking whether there is a state or not. Yes, there is a state S1 corresponding to 1. So S1, if I give an input of 1, it goes back to S1. See, okay. Now we successfully done for S0 and S1. We will see about S2. The two possible paths in S2 we will have is 0 and 1. If we put 0, it will become 1, 0, 0. Because S2 we already have 1, 0, right? See. Okay. In the case where we'll put give 0 input, go and check whether we have a state for 1, 0, 0. No, right? Now I'm going and dropping this one and considering only the other two values and checking again whether we have a state for 0, 0. No, right? I'm so going again and dropping one more value and considering only the rightmost digit, we will get like only have 0. Going and checking again whether there is a state. No, right? There is no state. If there is no state at all, so we will be removing this digit also. So if we have no state at all, then we'll directly go to S0, right? The reset state. So we will go to S0. So S2, whenever we give an input value of 0, it goes to the state S0. Now let's discuss the other case where we will give an input 1. When we give an input 1, the sequence will become 101, right? Go and check whether we have a state for 101. Yes, we do have a state for 101, which is S3. So S2, whenever you give an input value of 1, S2, whenever you give an input value of 1, it goes to the state S3. Now we will discuss about the last and final state. Okay, our sequential circuit should detect continuously. It's not like once I detect, I will turn off. Like every digital or sequential circuit we are going to make, like it will work as long as we provide the clock input. So we will start with S3. S3 already state already have a number like a value of 101, right? It's our like final state. After going to the final state, there are again two paths, 0 or 1. If I put 0, the number looks like this. See there, but there is no state corresponding to this 4-bit binary number. So I'm going to drop the leftmost bit and consider only the rightmost 3 bits, and I will left with 0 1 0. Again, there is no number state for 0 1 0. So I'm again going to drop the leftmost bit and only consider 1 0. Going again and check whether we have a state for 1 0. Yes, we have a state for 1 0, which is nothing but S2. So I'm putting it as S2. Whenever from S3, whenever we give an input of 0, it goes to S2. See, we are in S3. We are giving an input of 0, it goes to S2. Again, there is other case where the input can be 1, right? In that, if we give an input value 1 from S3, it will become something like 1 0 1 1. But we don't have a state for this 4-bit binary number. See, so I'm going to drop the leftmost bit, that is 1. I'm considering only 0 1 1. And I'm going to check again whether we have a state or not. We have no state, right? Corresponding to 0 1 1. No state. So I'm going to again to drop the leftmost bit, that is 0, and consider only 1 1. And going again and check whether we have a state for 1 1. No. So going and again dropping the leftmost bit, only considering the other one. And yes, we have a state for 1, which is S1. So here it goes directly to S1. Not directly, it goes to S1. Okay. From S3, whenever we put a value of 1, input value 1, it goes to the state S1. See, S3. From S3, I'm giving an input value of 1. It goes to the state S1. Now I'm going to discuss the number which is written inside the circles below the state name, right? Okay. These numbers are nothing but the output values. Our circuit needs to detect the sequence 101, right? It should detect the sequence only when all the numbers are successfully how to say successfully detected by our circuit. Like successful detection only takes place in the state S3, right? See, S1 does not match with our sequence. We have nothing. S1 is just 1. S2 is 1 0. But only at S3, our full sequence is like completely detected. So I'm going to give output value 1 whenever we reach S3, and in the rest of all the state cases, the output value will be 0. If you guys have, that's all. This is our state diagram. We first convert our logic into break our logic into uh, different states or levels, and like and define the paths where each input values gets us to. And in this case, we are having 4 states, right? So 4 states means we need to have 2 flip-flops. As in the earlier session, we already dealt that already we learned that a flip-flop can only hold 2 values, 0 and 1. But 2 flip-flops together can hold 4 values, 0 0 0 1 1 0 1 1. Like for state yes, we can consider it as 0 0. State 1 we can consider it as 1 0 0 1. State 2 1 0. State 3 1 1. So this is the actual state diagram part of the circuit. If you guys have any doubt, you can ask.
I have a doubt.
Yeah, tell.
So here we had 101. So what if we have, let's say, 1001, or like any
Yeah,
four
you can
digits?
have. Yeah, you can it's not necessary that you should finish everything in 4 states. Like
Yeah.
you should be. Yeah, we can go for more states.
So
In case we are going for. Tell.
the process will be similar only, like to drop the leftmost digit after
Yeah, yeah,
anything.
yeah. Yeah, you should first check the digit as it is, if none of the states are matching, you should drop the leftmost digit and consider the rest of the digits, and you should continue this process. If nothing else is matching and you drop every digit, you will go to the reset state or beginning state. Yes, the logic is similar for everything. You can also even build circuits like with 10 states and all, but it like you should be careful for not making some careless mistakes. Is it okay?
Yeah, I understood.
Yeah, okay. Okay. Having said the like having discussed the state diagram representation of our circuit, we are going to jump into the actual our sequential circuit. Okay. Now from this, we have successfully we had a plan, we had a logic of how our sequential circuit should work. We converted our logic successfully into a pictorial representation. Now we are going to convert that pictorial representation into an organized form of data known as state table. State table is nothing but like in combinational circuits, we have dealt with the truth table, right? Similarly, in case of sequential circuits, we will deal with state tables. As I told you earlier, since in this case we have four states, we need to represent them distinctly. So I'm going to have two flip flops, QA and QB, like A and B, whose values present state values are denoted by QA of t and QB of t, and X is our input value. And again, QA of t plus 1, QB of t plus 1 are the next state values. We are going from one state to next state, right? The state where the arrow begins and state where the arrow ends, arrow begins is present state, and the state where the arrow points to is the next state. And y is the value that we have written inside the circle, right? So same value of y. Now I'm going to represent S0 as 0, 0, S1 as 0, 1, and S2 as 1, 0, and S3 as 1, 1. It's not necessary that you should uh, represent all the circuit in the exact same order. Like 0 means I took 0, 0, right? It doesn't matter. You can name you can name the circuit as ever you want, and but you should fill the truth table according to your own convention. Like for this session, I'm keeping the convention very simple. Like I'm say keeping fixing S0 as 0, 0, 0, 1, 1, 0, and 1, 1, which is simple to see. Okay. Now in truth table, we have an input values and we will write all possible combination of inputs, right? Similarly, I'm going to write the present state values QA of t, QB of t, and x, and write all combination of all possible combinations from 0, 0, 0 to 0, 0, 1 to 0, 1, 0 to 0, 1, 1 to 1, 0, 0 to 1, 0, 1, and so on up to 1, 1, 1. Right. Now I'm going to write the corresponding values of the next state on output y. See in this state, yes, 0, 0 is S0, right? From S0, if I give an input value of 0, it will go to S0 itself, right? From the diagram, you can clearly see S0. If you give an input value 1, it goes to S0 itself. It goes back to S0, which is nothing but the state 0, 0. And the output value will be only be 1 whenever you go to the state S3. See, there is only one case where we go to S3. In rest of all cases, the output value will remain 0. Similarly, you should convert every data. Like first, you should read from this data what it says. So starting from 0, 0, giving an input value 1, and you should go check the diagram and mark it correspondingly. Mark the rightmost value, the next state values and outputs correspondingly. By doing so, you will get this state table. Are you guys okay with it? Do you guys understand how we build the state table? Have any doubt, you can ask. No?
Can you tell what is A and B?
A and B are nothing but just a name for flip-flops. I told you, right? We have four state. We need to represent the four state distinctly, right? And a flip flop can like have an two distinct values, 0 or 1. So we are planning to take two flip flops so that together they can represent four different values, right? 0 0 0 1 1 0 and 1 1. So I'm taking two flip flops A and B. QA is the present state value of that particular flip flop. QB is the particular present state value of the flip flop B. Is it okay? Now you can understand, right? Okay. Now we have like considered all every other like every cases and successfully built our state table. Now you guys, I think you guys can remember this table from last session. This table is nothing but the excitation table for D flip flop. Since you guys are familiar with D flip flop, in last two sessions we have built two examples with them, right? So the two flip flops, we need to use two flip flops in this for this state diagram, right? For this machine, a sequential circuit. I'm using D flip flop for this case, like for our problem. So that first I'm writing the excitation table for D flip flop. And see, excitation table is nothing but I give like you will have the present state value Q of t and next state value Q of t plus 1 and guessing like what input should be that we have given to D so that like the exact like the exact order matches. See, but remember one thing, easy thing for D flip flop. Just see both Q and D, Q of t plus 1 and D are same, which is the characteristic of D flip flop. We have seen, right, the characteristic equation of D flip flop is Q of t plus 1 is equal to D. See, both columns are exactly matching, right? 0, we have 0 here, 1, 1, 0, 0, 1, 1. So I'm going to like this is the state table we had, right? QA of t, QB of t, and like present state and next state, right? We are going to like from this present state and next state. I'm going to guess what value of like what is the value that I should have given to D so that this happens. So I'm writing, I'm adding other two columns to our truth table, sorry, state table, namely D of A and D of B, which are the inputs we give to the D flip flop. See, for this, like one simple trick is to, for DA, we just need to copy QA of T plus 1 row, column, exactly 0, 0, C 0, 1, 0, 0, exact same copy. 1, 0, 0, 1, 0. Same goes, you should write entries as we entered for QB of T plus 1. Okay, this is the completed version of our state table. Now, like now using K maps, we will be finding expression for Y, DA and DB using in terms of QA of T, QB of T and X. Like in sequential circuits, the output values are the functions of present state values and output state. Similarly, we are going to do that. Here, I already calculated the calculated and evaluated the expression for Y TA of B and DB of T using K maps. This will be available to you guys after the session. You can sit back and you can try it on your own. Okay. Now we are going to simulate the going to build the sequence detector in logism. For that, first of all, have you guys downloaded the logism file I've sent in the group? Name like a drive link I attached to the message, right? Have you guys seen it? Seen and downloaded the file? Hello?
Yeah.
Yeah. Okay. If you have downloaded the file name will be session 5 workspace. Okay, this is the workspace or file we are going to build all our circuits in this session. So open the circuit, go over the like session 5 workshop workspace, right click, you will have an option of add circuit. type the name of the circuit. We are going to do a sequence detector, right? So sequence underscore detector and hit enter. Now make sure that there is a small arrow, right? Like a magnifying glass. Make sure it's above your sequence detector circuit. Now, as I told you, we drop the memory file, take two D flip flops and place it over here. Now name them. We are naming. We are given name as A and B, right? So double click the flip flops and enter the name like A and B. Now this is the flip flop A. This is QA of the value. This is D of DA. This is DB. That's all. Similar things. Now, like for I'm going to have we going to have an output value, right? Like sorry, external input. It's external input X. So I'm taking an input port and naming it as X and see the expression. The expression for DB is just X. So I'm directly connecting my input value that X to D of B, the input of the flip flop B. Okay. Now see the expression of DA of B. It's a bit complex, so bear with me. DFB is QB X bar plus QA QB bar X. So we will be needing two AND gates and one OR gate. So I'm placing two AND gates and an OR gate. And one of our AND gate as an like 3-bit input, as an 3-bit input. So I'm clicking over one of the AND gate and changing the input values to 3. You can change it in the leftmost, like leftmost bottom corner. You can change the number of input. So it becomes 3. So as you guys can remember the, like it's difficult to remember the long expression. So it's nothing but first we are going to connect QA of B. And after QB bar of T, the complement of QB. Uh, and you guys can know from the last session that this is the complementary version of the like complementary version of this Q. So I'm directly connecting using this. And the other term is X, QA, QB bar and X. And the other min term is QB and X bar. So going for we need X bar, right? So I'm going to have a NOT gate. So we have successfully gave the values for values for the flip flops input. Now we have one more expression for Y, right? See, QA QB bar X. So this is our output value. We need to have an output port. Name it as Y. And take a AND gate. AND gate. Place it here. It's a three input AND gate. So click it and go change the like number of inputs. And after that, the expression is QA of B. Sorry, QA. So I'm going to first connect QA. After that, QB bar. Finally, X. So we successfully connected the circuit, but we have forgot one more thing. We forgot to connect the clock. So I'm going to connect the clock. Instead of like going on and taking clock, just take another input port and place it here. Double click and name it as CLK for clock and connect this. I will tell you what we are exactly doing. Now connect the clock trigger inputs. Now we are done with the circuit. Now go and save it in whatever name you want. Okay. Now go to main, like double click the main circuit. And after going to main circuit, make sure that your glass is like there is a small icon over this circuit, and just like one click the sequence detector we just made and drag it to the workspace. Now go to the wiring, take a clock and place it. Now we need to it's a sequence detector, right? So we need something to generate a sequence of input randomly. So uh, just go and open memory. Under memory, you will have a circuit named as random generator, and go and place it in and place it in our workspace. Now connect the clock. We do have a clock input, so connect the clock. Connect the same clock to our sequence detector, and like if you click the random generator, it has a data bit, like in the leftmost corner you will have like an option of data bits. It shows 8-bit, but our like we should give it as 1-bit, because we are accepting only 1-bit entries, 1-bit value as input. So and after hitting enter, make sure that data bit is 1, and after that connect this point, like this port to X, and like have an output port and connect it to Y, and name it as however you want. Name it as OP, meaning output. Okay, this is our sequence. Like we also set up our test bench for sequence generator, and now we are going to go to the simulate. Click auto tick enabled. The clock will start to work, and the random generator will generate random sequence of binary inputs. And our sequence generator is going to detect whenever it sees 101. Now go to the same simulate option. After the clock tick and all, you will have an option of timing diagram. Go and click it. Under this timing diagram, you will have an many options. Like to the right of the option, we will also have an option of timing diagram. Go and click the timing diagram and see our circuit is working, right? Okay, this is the timing diagram. I'm going and pausing on the simulation and tell you guys the how it works. Now this is the clock input. We don't need to see this. The random generator generates in random sequence of numbers. See there, generates 0, 1, 0, and continuously like generates 0 for some times, and after that it generates 2 for 2 like generates 1 for 2 times, and after that it goes to 0, 1, 1. See, from 1, 0, 1. It's our sequence rate. So it detects the number as 1. Like it detects the sequence. So our output value will be 1. Similarly, see this. Whenever you have a dip like this, like from 1 goes to 0 and again goes to 1, we will detect the sequence of 1. And you can resume the simulation and see how it works. If you guys have any doubt, you can ask. Any doubts in the timing diagrams and any doubts in the circuit, you can unmute and ask me. See, it again detects two sequence. See, whenever we have a dip like this, from 1, it goes to 0 and again goes to 1. Our output, like our sequence detector, will detect it. Again, also the next time, it again goes from 1 to 0 and again to 1. So, like not having two zeros, only 1 0. Like this line represent 1 0. But these two lines represent we have 1 1 0 1 1. But we have 1 0 1, right? If we go and check the last three inputs, it will be 1 0 1. So it detects. If you guys have any doubt, you can also write it in the chat box. You can also unmute and ask if you are facing any problems in the simulation. So no doubts, right? Okay. If you guys are done with this circuit, please type in type ready in the chat so that we can go to the next topic. Okay. Since we had no doubt, we'll be seeing the concept of counters. Santosh, go on.
Hello everyone. Now we'll start with the topic of counters. I'll share my screen first. I hope the presentation is visible. The screen share visible.
Yes. Yeah, it is visible. You can go on.
Yeah. And now we'll start with counters. We'll discuss what counters do, and then we'll move on to logism. We'll build different types of counters. Because what are counters? A counter is a sequential circuit that goes through a predetermined sequence of binary states. So a counter is just a sequential circuit. It goes through some determined binary states again and again. It's like let's say there is a counter. It goes through some 4 states again and again. And let's say it goes through 0 0 0 1 1 0 1 1. And again it goes through 0 0 0 1 1 0 1 1 after repeated intervals of time. So as it goes through a predetermined sequence of states in a repeat in regular intervals of time, we can use it to count some specific events. Like we can fix a clock to it. We can count how many clock pulses are passed. We can even make it count numbers, and we can do stuff like that. So counters are made using flip-flops. So the most popular type of flip-flops used to make counters are T flip-flops. But T flip-flops are also used sometimes. We'll look at the later. But most counters are made using T flip-flops. And there are two basic kinds of counters. Asynchronous counters, they are called ripple counters, and synchronous counters. So the main difference between asynchronous counters and synchronous counters is, as we know that we use flip-flops in making a counter, in case of an asynchronous counter, the flip-flops will have different, each flip-flop will have a different clock connected to it. In case of a synchronous counter, each flip-flop in the system will have same clock connected to it. That means each flip-flop is synchronized with each other. So that's why they are called synchronous counters. We'll look at it in detail in a moment. before moving on to discuss the types of counters, we'll first discuss the excitation table of T flip-flops. As we use T flip-flops a lot while designing counters, it's a good time to learn about the excitation table of T flip-flops. So in the previous session, you would have learned about the truth table of T flip-flop. Whenever the input is zero, whenever the T flip-flop input is zero, the next state will be same as the previous state. Will be same as the present state. Whenever the input of T flip-flop is 1, the next state will be the complement of the present state. So by using that, we build a different table. Different table with 3 columns. The first column has the present state, it's represented as Q of T. And the second column represents the next state, it's represented as Q of T plus 1. The third column represents the input of the flip-flop. It is represented by T. So Q of T, as we are dealing with a single flip-flop over here, it can either store 0 or 1. So we just have 2 states. Now, Q of T can either take two values, 0 or 1, or Q of T plus 1 can either take 2 values, 0 or 1. So there are 4 entries in the table. There are 4 different possibilities. We'll consider these possibilities one by one. First, whenever the present state is 0, whenever Qt is 0, and whenever Qt plus 1, the next state is 0, the flip-flop input T is 0. That's what the first column says about. As the present state and the next state is same, the flip-flop input is 0. So moving on to the next state, when the present state is 0 and the next state is 1, the flip-flop input is 1. As you can see, the next state is the complement of the present state. The input of flip-flop is 1, it can be deduced like that. And whenever the present state is 1 and the next state is 0, the input of flip-flop T flip-flop is 1. As we can see, the present state and the next state are complements of each other. The input of T flip-flop is 1. Whenever both the present state and next states are 1, the input of T flip-flop is 0. Because they both are same. I hope everybody is clear with this excitation table. Do you guys have any doubts? Okay, so I hope everyone is clear with this. Okay, now we'll discuss the first type of counters. That is the ripple counters or asynchronous counters. Asynchronous counters are also called ripple counters. Okay. So in a ripple counter, a flip-flop output transition serves as a source for triggering other flip-flops. In ripple counter, we have a series of flip-flops. We use the output of one flip-flop as the clock of the another one. As the clock of the next flip-flop. So we can see that different flip-flops will have different clocks. That's why these flip-flops are kind of not synchronous with each other because they don't have the same clock. So they are called asynchronous circuits. So now we'll build a asynchronous circuit, and while building, concepts will get more clear. Okay, now we'll build something called a 3-bit ripple counter. So why it's called 3-bit? Because we use 3 flip-flops over here. This is the circuit diagram of the counter that we are building. Why it is called a 3-bit ripple counter? It's called 3-bit because we use 3 flip-flops, and each flip-flop can store it can store 1 bit of data. It can either store 0 or 1. And it's a ripple counter. It's an asynchronous counter because as you can see, these 3 flip-flops, they have different clocks. The first flip-flop, which is named as A0, we have the clock connected to it. And the second flip-flop, A1, has the complemented output of A0 as its clock. The output of A0 as the complemented output of A0 is connected to the clock of the next flip-flop. And the complemented output of the A1 flip-flop is connected to the clock of next flip-flop. So you can see that these 3 flip-flops are different clocks. So this is called an asynchronous counter. Now we'll actually build one asynchronous counter using logism. I hope you guys have downloaded this file which was sent, which is uploaded in the drive, the workspace. Okay, this is the workspace that's been uploaded by us. Is my logism window visible?
Yes, it is visible.
Okay. So now we'll create a new circuit. In the session 5 workspace, right click and click add circuit. And we'll give our name as ripple counter. Now double click this ripple counter and we have an empty workspace which we are ready to build our counter. So now go to the memory section in the left pane, double click it, and you'll find T flip-flops. We need T3 flip-flops over here. Just click once, place one over here. Place 3 flip-flops in the left plane into the workspace, like this, like this. Okay, so yeah, we'll first name all these 3 flip-flops. We'll name the lowermost flip-flop as A0. I'll let you know the reason for naming later when we see the working of flip-flop. Let's name the middle flip-flop A1 and the upper flip-flop A2. Okay. Now in the left hand side pane, under the wiring section, there is a clock over here. Just click the clock, drag it over here, and connect it to the clock port of the lowermost D flip-flop. I mean the A0 flip-flop. You can just drag this over and connect this. Now we have these we have these 3 flip-flops with 3 inputs. We have these T terminals in each flip-flop. These are the input of these 3 flip-flops. Now we'll connect all these inputs together and we'll provide and we'll make sure that all these inputs always stay high. So we now under the same wiring section, you can see an option called constant. If we connect these wires to this constant, it means that the terminals always stay high. As we have connected all these 3 input terminals of these 3 flip-flops to the one, it means that all these 3 flip-flops will always get input 1, no matter what the output or clock signal is. So I can just drag it over and connect this. And now we connect the complemented state of each flip-flop. We connect the complemented state of each flip-flop into the clock of the next one. So we connect the complemented state of the flip-flop, I mean the A0 flip-flop into clock of 1. And same thing we also do for A1 flip-flop. We take its complemented output, we connect it to the clock of the next one. Okay. Now we have these 3 output terminals, the Q. We take these as output terminals. So now let's go to the input output section. We'll take LEDs. We'll take 3 LEDs. We can just place these. We can just connect these LEDs to the output terminals of the 3 flip-flops. Yes. So yeah. Now our circuit is ready. Now we go to the simulate option. We can click this auto tick enable. It enables the clock and the clock starts sending its signal. Okay, I will explain. I will now we'll stop the simulation. We'll now put a oscilloscope and see how exactly it counts. We'll put an oscilloscope to analyze the signals and see exactly how it counts. Now let's go to the input or output extra. We'll take this oscilloscope under this. We'll paste it here. And now we have 3 input ports of these oscilloscopes. Now, if we just send these, if we just send these output, connect this output and input terminals, it will show the waveform of how it exactly behaves. We'll take one from the clock and connect it to the first terminal. Okay, so the next one is now we'll take the output terminal from A0 and connect it to the second pin of oscilloscope. Can also move this oscilloscope. Yep. Now we'll take the output pin of the second flip flop A1 flip flop and connect it over here. And now we'll take the output pin of this A2 flip flop. We'll connect it to the input of the oscilloscope. Okay. Now again, let's go to the simulate window. Let's start this auto tick enable so that the clock starts running. As you can see, the clock generates different timing diagrams. I pause this clock. As you can see, in the first row, we connected this to the clock. So the clock generates 0, 1, 0, 1. It generates 8 cycles like this. And now the second output, if we consider the first clock cycle, if we just consider this first clock cycle, we can see that A0 is 0, A1 is also 0, A2 is also 0. So in binary representation, if you take A2 as the most significant bit, and if we consider A0 as the least significant bit, you can see that this represents the binary number 0, 0, 0. Now, if we move on to this clock cycle 1, we can see that A0 is 1. You can see high or this A0, and A1 is 0 and A2 is 0. So if we consider A2 as MSB and A0 as LSB, we can see that it represents the number 001. So 001 in binary is 001 in decimal is just 1. So similarly, if we see in case of the second clock cycle, we can see that this first one A0 is 0, A1 is 1 and A2 is 0. So it represents the number 010, which in decimal is 2. Now, in case of the third one, we can see that it represents the number 0, A2 is 0, A1 is high, and A0 is high. So it represents the number 011. So in decimal, we can see it represents 3. Now, if we analyze these waveforms in a similar way, we can see that it counts from 0, 1, 2, 3, 4, 5, 6, 7. You can see over here, all these 3 are high. All A0 is high, A2 is high, A1 is high, and A0 is high. So it represents the number 7. And again, A0 is 1, A1 is 1, and A2 is 1. So it comes down to 0 again. You can see that this counter counts all the way from 0, 1, 2, 3, 4, 5, 6, 7, and then resets. It goes back to 0 again. So this is how a 3-bit triple counter works. It counts all numbers from 0 to 7 and then resets again. Now if we play the simulation again, you can see the LEDs denoting the binary. We can see the LEDs which denote the binary number 000, 001, 010, 011. I'll reduce the speed so that you can see better. Let's go to the auto tick frequency. Let's reduce the frequency. Let's reduce the frequency to 1 Hertz. Okay, so you can see 000, 001, 010, 011, 100, which is 4, 101, 5, 110, which is 6, and 111, that's 7. Now it resets. It comes back to 0 again. So it starts counting again. So that's how a 3-bit triple counter works. So if we want to count numbers from 0 to 15, if you want to count numbers from 0000 to 1111, we can add an extra T flip flop like this, and we can make a 4-bit triple counter. So depending on our rates, we can add or reduce flip flops so that we can count to the required number. I hope everyone is able to follow this logical simulation.
Yeah.
So I guess it's a good time to take a break. We'll continue in 5 minutes. Let's take a break. I guess now let's continue with the session. Is my screen visible?
Yeah, it is.
Yeah, okay, so now we are seeing how these signals, how this counter actually works. So our next step is to we'll add a 7 segment display. We'll see, we'll make this counter display numbers in the 7 segment display. So before that, we need to learn what a 7 segment display is. Let's go to the slides. Okay, so we'll see what a 7 segment display is. 7 segment display is a series of 7 LEDs. These 7 LEDs, each LED is called a segment, and these 7 LEDs are arranged in such a way that uh, if we make certain LEDs glow, we can make them represent all numbers. I mean all numbers from 0 to 9. So this is a 7 segment display. These curved rectangular parts are the LEDs. There are 7 of these LEDs, so this is called a 7 segment display. And these LEDs are named as A, B, C, D, E, F, and G. G is the center one. So, for example, if you want to display 0, we can make the LEDs A, B, C, D, E, and F glow, and we can get G in off state. So if we do that, we'll be able to display 0 in some segment in the 7 segment display. So for example, if we want to display the number 8 in 7 segment display, we have to uh, we have to make sure that all these LEDs are in on state. All these segments A, B, C, D, E, F, G are in on state. So this is what a 7 segment display is. Uh, we'll make different segments of the LED glow at the same time to represent different numbers from 0 to 9. Okay. So in order to connect the ripple counter to a 7 segment display, we need a kind of bridge in the between. A bridge in the between which decides which takes in the binary values it decides it decides which LED segments should be turned on so that we can represent the particular number. So this BCD to 7 segment converter is a circuit block which does that. So it acts as a bridge between the input and the 7 segment display. So it takes the input bits, decides which segments of the display should go to represent that number. For example, if we input the bit 0, 1, 1, so 0, 1, 1 in binary is 3. So if we input these bits, okay, this is a 4, it takes a 4-bit input, so we'll input 0, 0, 1, 1. 0, 0, 1, 1. So 0, 0, 1, 1 is in decimal is represents the number 3. So this BCD to 7 segment is a combinational circuit. It decides to display number 3 in the 7 segment display. What LEDs should I turn on? So it decides all. It makes all these calculations inside. It decides, and it releases the outputs from these output ports. These output ports are named A, B, C, D, E, F, G, which will connect to the seven input ports of the 7 segment display. We'll see how exactly do we do this in logarithm in a minute. First, we'll learn how this works. So A0 is the LSB, the least significant bit, and A3 is the MSB, the most significant bit. So it has 4 inputs. It takes 4 input bits, and it outputs 7. And it outputs 7. Okay, now we'll connect this ripple counter to the BCD to 7 segment display. And this BCD to 7 segment display will connect it to the 7 segment display over here. As you can see, this circuit block acts as a bridge between the ripple counter and the 7 segment display. Now we'll do that in logarithm. Is everyone clear with this BCD to 7 segment converter and the display?
Yes, it is clear.
Okay, now let's move on to logarithm, and we'll do that. Okay, now we'll take up this oscilloscope, and we'll also clear these connections. We'll make new ones right now. You can just select it. We can just click delete so that we can clear all these connections. Okay, so on the workspace which we have sent, we have already made this VCD to 7 segment converter the block. We already have it here. It's in the name of the 7 segment driver. We can just single click it and we can drag it into our workspace like this. It's already there. We just single click it and we just drag it into our workspace. Okay.
In which
So
counter is
yeah,
there? 7 segments.
in session 5 workspace, in the file which we have sent in the Google Drive. It's under the session 5 workspace, along with main 4-bit comparator and other files.
No, I'm asking this 7 segment driver.
Can I repeat your question
No,
again? No, it is the same BCD to 7 segment converter which we discussed. It's
Okay,
also called a
okay.
driver. It's the same circuit. Okay, so now in this circuit, Z is the LSB, the least significant digit, and W is the MSB, the most significant digit. So we have built our ripple counter to count numbers from 0 to 7. So the binary states go from 000 to 111. So we can this W, the MSB always stays 0. So we can go into the wiring section. We can take a ground. We can take a ground. We can just connect it to the W part. This W part is the MSB, so it always stays 0. So we just connect the ground to make sure that it always stays at 0. Now the LSB, the LSB will connect to the terminal C. We'll connect the middle digit to the terminal Y, and we'll connect the MSB to terminal X. So now we are done with the inputs of the 7 segment, the BCD to 7 segment converter. And now under the input or output section, under the input or output section in the left hand side pane, there is a device called 7 segment display. We can just click it and drag it over here. If you just hover your cursor over these points, we can see the name of the segments. This is segment G, and this is the segment F. This is segment A, and names are displayed. So we can just see the names and connect these to the outputs over here. So segment G, I'll connect it over here. I'll connect segment F over here. So this is segment A. So we can just connect this segment A to the segment A of the 7 segment display. So this is the segment B. We can just drag it over and connect it to here. So this is the segment E. We can just drag. We can just take a wire from segment E. We can connect it over here. And this is segment D. We can take a segment from D. We can connect it over here. Yeah, and the remaining segment is segment C. Now, there are, if you notice, there are actually eight input terminals, and we have left this input terminal unconnected because this input terminal is used to represent decimal point. So if we connect this terminal, we can use this to generate the decimal point over here, which we can see is a small dot. As we are just representing integers, we don't need a decimal point, so we just don't use it. Now, if we go to the simulate option, if we click this automatic enabled option, I will start the clock. And yeah, we can see the circuit running 0. And as you can see, the numbers also get displayed in the 7 segment display as the ripple counter counts up. 5, 6, 7. And then it resets again, it goes back to 0, 1, 2, 3, 4, and it goes like that, and it keeps on repeating. So is everyone clear with this part? Have you guys done this?
Sir, where I'll get this 7-segment display? BCD
Under the
converter.
input or output? BCD converter. This 7-segment driver.
Are you asking about the 7-segment display?
This
Hello?
display are you asking?
Not display. This one.
Driver.
BCD converter. Yeah.
Yo, have you downloaded the drive link? Gone to the drive link and downloaded the file. .crc file we have sent. Hello?
Okay. That I have
Yeah.
downloaded.
Okay. It's given in that circuit.
Okay.
So you can directly work in this circuit.
It's there under session 5 workspace. The 7-segment driver one. It is the unit which we are using here.
Okay.
Okay, so shall we move on to the next type of counter? Do you have any doubts? Anyone?
Can create this 7-segment driver manually.
Can you repeat your question again?
This 7-segment driver we have created manually, like
Yeah.
Yeah, we created manually and added the circuit so that you guys can easily build this circuit. It will be very much difficult if you also build that 7-segment circuit from scratch in this session. We don't have enough time, right?
Yeah.
That's why.
It will be a bit
You can
lengthy,
build.
but it's doable.
Yeah. You can try it after this session if you want.
It's doable, but bit lengthy. It takes time. It takes some time. That's why we have done it. Okay, so moving on. We'll move to the next type of counter. So what we have done in logistics simulation is an asynchronous counter. It's a ripple counter. As you noticed, we have used different, each flip-flop has a different clock. So we have done a ripple counter. Now we'll talk about synchronous counters. Okay, synchronous counters. Yes, it's everything is same as the ripple counter. We use T flip-flops mostly to do it. But the only main difference is we use the same clock circuit for these 3 flip-flops. So as you can see, a common clock triggers all flip-flops simultaneously rather than one at a time in succession as a ripple counter. So we use the same clock to trigger every flip-flop. So we can say that all the flip-flops are kind of synchronized. So that's why these are called synchronous counters. Okay, so now we'll build a synchronous up counter. It counts from the state 000 to 111. It's kind of the same counter same ripple counter which we built, but we'll do it in a different way using the same clock for each flip-flop. Okay, so now you can see this is a comparison between asynchronous and synchronous counter. And so this is the circuit which we built in Logism. And this is the circuit which we are going to build in some time, which we'll do in some time. The 3-bit synchronous counter. As you can see, these 3 flip-flops have different clocks. It has the main clock. The input of this is the output of this is fed up to this. Its output is fed up to this. And while in this circuit, we can notice that all these 3 flip-flops have a common clock. So we'll build this in some time. We'll first understand how it works. Now, so this is the state diagram for 3-bit synchronous up counter. So we have 3, if we just count this number of states in the state diagram, we have 8 states. So we use 3 flip-flops. As each flip-flop can either store a 0 or 1, we use 3 flip-flops. So there are 8 possibilities. So we can see that this state diagram has 8 states. So the circuit can be represented by a 3 flip-flop system. So let's assume this is the initial state 0 0 0, and after a clock pulse, it goes into the state 0 0 1, and after a clock pulse, it goes into the state 0 1 0, and similarly it goes into states like 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1, and after it reaches its full count, after a clock pulse, it goes back to its initial state 0 0 0. So this is the state diagram of circuit which we are going to build. So in a way you can see that this counts all the numbers from, if you convert everything into decimal, we can see that it counts numbers like 0, 1, 2, 3, 4, 5, 6, 7, and back to 0. Okay. So now as we've done the state diagram, our next stage is to do the state table, and then after doing the state table, the next step is to derive the inputs of flip-flops and then realizing it in logic. So we're done with the state diagram. We understood how the states progress as this how the circuit behaves. Now let's move on to the state table. Now we use three flip-flops. We just name these three flip-flops as C, B, and A, B, and C. And we can see there are 6 columns in the state table. The first column QC of T represents the present state of C flip-flop. Remember we have named the flip-flops as ABC. So this second column represents the present state of flip-flop named B. So this third column represents the present state of flip-flop named A. This column represents the future, the next state of flip-flop named C. This column represents the next state of the flip-flop named B. And this final column represents the next state of flip-flop named A. So as you can see, the first 3 columns represent the present states of the system, and the next 3 columns represents the next states of the system. I mean after one clock edge. So we can derive this directly from the state diagram. So when the present state is 0 0 0, we can just look on this first column. If the present state is 0 0 0, the next state is 0 0 1. As we let's from the state diagram we can see that when the first state is 0 0 0, the next state is 0 0 1 after one clock pulse. So we have done exactly the same thing over here. Present state is 0 0 0, next state is 0 0 1. If the present state is 0 0 1, it goes on to the next state 0 1 0 after one clock cycle. So in a similar way, we can do this. If the present state is 0 1 0, the next state is 0 1 1. If the present state is 0 1 1, the next state is 1 0 0. And in a similar way, we can fill this whole state table. Now, if we have a look at the last column, if the present state is 1 1 1, so 1 1 1 is the final. I mean, it's the after 1 1 1, in the next state, the flip-flop the system gets reset. So if the present state is 1 1 1, if we just see the last column, the next state is 0 0 0, because after counting up to 1 1 1, the flip-flop gets reset. It goes back to 0 again. So this is a state table. I hope everyone is clear with this.
Yes.
Okay, so now let's move on to the next step in realizing this circuit. Now we have seen about the excitation table of T flip-flop over here. This is the excitation table which we discussed a few slides ago. So as we have 3 flip-flops, we know their present state, we know their next state. So using the present and next state, using the excitation table, we can derive their inputs. We can derive the inputs of flip-flops. So this is the same as the previous table, but I have added 3 more columns. We can see these columns TC. TC represents the input to the flip-flop C. TB represents the input to the flip-flop B, and TA represents the input to the flip-flop named A. So let's consider a single flip-flop. Let's consider this flip-flop named C. So this TC, from the excitation table, we can see that this TC can be derived if we know QC and QC T plus 1. So we know QC is 0 0 0 0 1 1 1 1, the first column. We have this QC T plus 1, which is 0 0 0 1 1 1 1 0. So if we just apply this excitation table, we can get these inputs of the flip-flop named C. We can get this whole column. So let's do this. If you see the first row, QC, the present state is 0. The next state is also 0. So the input of T flip-flop, input of the TC is 0. Now if we go to the second row, present state is 0, the next state is 0, so the input is again 0. So similarly, we can do this for every entry. Let's consider this last entry. If the present state is 1, next state is 0. So as you can see, the next state is complement of the present state. The input of C flip-flop is 1. So in a similar way, we can derive this column for C. Similar way, by considering QBT, this is second column, and the fifth column QBT plus 1, the present and the next states of B flip-flop, we can derive TB, and we can derive TA by considering QAT, the present state of A flip-flop and the next state of A flip-flops. Now, if we just use this table and derive this, we can notice something. TA is we can get these expressions. We can get these expressions. Yeah, if we notice something, we can see that TA is always 1. So we don't need to use K maps for this, and we don't need to use K maps for this and simplify. We can just directly do it using our mind. So you can see TA is always 1. So the expression for TA is 1. It's just 1. So irrespective of the input, irrespective of the present state and future state, it stays 1. So it doesn't depend on either QA, QB, or QC. Now, if you see this column for TB, you can see the 0, 1, 0, 1, 0, 1, 0 in this pattern. Now, if you look at this a bit more carefully, we can see this column is same as the present state of QA. If you see this column, we can see the same entries 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So we can directly see that TB equals QA because both these columns are exactly same. We get the same entries. We get the exactly same entries in both these columns. So by directly seeing, we can reduce this. And now TC also can be directly reduced as the AND operation of QB and QA. So if you consider these two columns, the column 2 and column 3, which represents the present state of B and the next state of B, if you perform an AND operation over here, so both of these zeros are 0, so AND of these is 0. So both of this one is 0, so AND is 0. You find a 0 over here, so AND of QB and QA is 0. Now in the fourth entry, both QB and QA are 1. So QB and QA is 1. We can see that in TC, first 3 entries are 0 and the fourth entry is 1. Now in a similar way, if we proceed, when QB and QA are both 0, the AND of both is 0. So the AND of this is 0. And for this 0 and 1 is 0, and AND of this 1 and 0 is 0. But in the final entry, we can see that when QB is 1 and QA is 1. So the AND operation between QB and QA is 1. So if we compare this table, the AND of QB and QA with this TC column, we get the exact same entries 0001 and 0001. So by this we can conclude that TC equals QA and QB. But we can also do this using K maps, but K maps it takes more time, and this is pretty simple to do. So we can just directly do this in our mind. So is everyone clear the expressions TA, TB, and TC how they came?
Yeah, it is clear.
Yeah, okay. So now using this, using the expressions that you have derived, we can make a circuit using T flip-flops, gates in logism. Let's move on to logism. It's my logism window visible.
Yeah, it is visible.
Yeah. So in the session 5 workspace, right click and create a new circuit. Let's create add circuit. And you can give any name which you want to. I'll just give it synchronous counter. Okay, now we get a new workspace to build a circuit. Okay. So now first, let's go to this memory section and let's take 3 T flip-flops. As we're using T flip-flops in a 3 T flip-flops in our circuit, we need to get these 3 T flip-flops out. Okay, so now let's name these flip-flops. Let's name this flip-flop as C. And let's name this as B. And let's name this as A. So this is the same naming convention which we used while discussing the state table. We consider three flip-flops, right? A, B, C. So we have named these three flip-flops A, B, and C. Now, the first thing we'll do is, as we are building a synchronous counter, we need to give same clock to all these three flip-flops. So let's extend the clock. Let's extend the clock pins of the three flip-flops. We'll connect it together like this. And now under the wiring section, click on this option, this clock, and give it to this wire order. And now we have connected same clock to this three flip-flops as we're making a synchronous circuit. And let's let's make the output. Let's make the output pins first. So this Q pin of A flip-flop is called QA. This Q pin of this B is called QB, and this QC is this Q pin of C flip-flop is called QC. So these are the output pins. These are the things which actually will connect LEDs, and they actually display numbers. So first we'll extend this. We'll connect three LEDs to mark the output terminals. We'll make three LEDs. So we can just place three LEDs. We can extend the output terminals. We can just connect them. So our next step is to we'll see what are the expressions which we got, and now we'll realize them using logism. So as I remember, we got TA as just one, right? So irrespective of the next state and previous state, it always stays one. So we'll get. So under the wiring section, we find this constant, right? We find this constant one. So we can just take this over here. We can extend the input of flip-flop, we can just give this one to the input of flip-flop here, as we've seen that TA is one. Now, if you see the next expression, TB is equal to QA. So now we have to give the output terminal of the first flip-flop into the input of the next one, because that's the expression which we got while deriving this. So next step is to take this output of A flip-flop. We will just give it directly into the input of the next B flip-flop. So now TA is 1, TB equals QA. And the next step, and TC is QA and QB. So to give the input of TC, we need an AND gate first, and the inputs of AND gate will provide QA and QC. So we'll take this QA over here. We'll take this QA, we'll put it into one input of the AND gate. And now we'll take this QB, we'll put it into the another input of AND gate. Now the output of AND gate should be connected to C. So now that's what we'll do. So this whole wire is Q. Now let's place an AND gate first. And let's connect its output to the input of this one. Now this whole wire is QA. So we'll take take a branch from the wire. We'll connect it to one of the inputs in the AND, one of the inputs of the AND gate. Okay, so we have connected QA into the AND gate. Now this is this terminal is QB. Now we'll take a branch from this QB. We'll extend this. We'll connect it to the second input of the AND gate. So yeah, we are done with the circuit. You can see that we use the same clock. TA is 1, TB is QA, and TC is QA times QA and QB. So now let's go to the simulate option. Now we'll click this auto tick enable so that the clock starts running. Okay, so one more thing I need to tell. This C represents the MSB. This A represents the LSB. So if I pass this clock now, so if this LED doesn't glow, it means that QC is 0. So when this LED glows, it means that QB is 1, and if this LED is 1, it means that QA is also 1. So this circuit represents 0, 1, 1, whereas QC is MSB and QA is the least significant digit. So when this represents 0, 1, 1, it means that in decimal equivalent, it represents 3. I'll just reduce the speed of clock once. Okay, I'll start the simulation. I'll continue the simulation now. So this is 100, it represents 4 now. 101, it represents 5. 110, 6. 1117. Now it gets reset 000, 001, 010, 011, 100, 101, 110, and 111. And it again goes back to 0 and it gets reset. And in a similar way, we can count, we can use a 3-bit synchronous counter to count all states from 000 to 111. So in case if we want to count all the states from 0000 to 1111, we just need to extend, we just need to put one flip flop. We need and if this thing can be extended to any number of flip flops, so that depending on the range which we'll be counting. So is everyone okay with this? Is everyone able to do this and follow this? Okay, so assuming everybody is clear with this, I'll move on. And now we can do one more thing. As you notice, this is up counter counting 111. I mean, after every clock pulse, the output of this system increases. It goes from 000, 001, 010, it increases. Now, by doing a minor modification to this circuit, we can make it count down from 111, 110. We can make it count down from 7 to 0. So we'll do that minor modification in this circuit and we'll make it a down counter. So now we'll stop the simulation. So we can just remove these output terminals. And now we'll just connect these LEDs to the complemented outputs. We have connected those LEDs to the normal outputs QC, QB, and QA. Now we'll connect this to the complemented outputs QC dash, QB dash, and QA dash. In this way, we can make this same circuit. We can make the same circuit count down from 111 to 000. We can make it count in the reverse order. So we'll connect this LED to the complemented output. And we'll do the same thing for flip-flop A. And now let's start the simulation again. Automatic enable. Yeah. This is 011, 010, 001, 000. As you can see, it's reducing from 111. You can see it's 111, 110, it is 6, 101, it's 5, 100, it's 4, 011, it's 3, 010, it's 2, 001, it's 1, and 000. And it goes back to 111 and it counts in the reverse order from 7 to 0. So this is called a down counter because it counts in the reverse order. So I hope everyone is clear with this up counter and down counter.
Yeah.
Okay, now we'll move on to the next topic. This is the down counter which we did. We just connected these outputs to we just connected complemented outputs to these LEDs. And now we'll move on to the next topic, ring counter, and Irvin will take on. I'll stop presenting now.
Okay. Is my screen visible? Hello?
Yeah, it's visible.
Yeah, okay. Now we are going to see two types of two types of synchronous, namely ring counter and Johnson counter. Like these are some special types of counters, uh, which is made by like connecting flip flop as a ring. See, we are connecting it in a ring-like shape, right? We are connecting the one flip flops in output to next as an input to other flip flop. We will particularly use D flip flop for ring counters. See, at last, the last flip flop's output is given as an input to the first flip flop, and it counts like this. It start to count from like the one moves like transmission rate. First one is there in D1, and after that this same one goes to this, and the one goes to this. Like this, we'll reach a state where it goes to this, and after reaching goes to the final state, it again goes to the first state, repeating this sequence. Uh, this is how a ring counter looks. Since we are out of time, I already built the encounter and I will show you how it looks like. Okay, this is the ring counter I made. It is exactly made as it's given in the presentation. I just added one more thing. Uh, in your session 5 workspace, there is an circuit known as 7-segment driver 2. It's not the driver 1. Actually, if you are using 7-segment driver 2, we can use connect two LED, 7-segment LEDs like this. Like you should connect this A0 B A0 to A0 B0 to G0 to the 0 bit, and A1 B1 C1 to the 1 bit 7 segment display. Now if I go and like as you guys can see here, we have a 0 value here. If I go and press 1, it will start counting. See, it started to count. Okay, once again. First of all, I need to activate the clock. Okay, it got activated. See, starts from 8 to 4, 2, and 1. Counts like this. Like ring counters are some special counters. We normally don't use them. Like we don't want to count in the order of 8. We generally use the ripple counter as it counts in our order in stopwatch, and that we count like number wise, right? We will count from 1, 2, 3, 4, 5. That like that only we are going to count, right? Ripple counter is one of the special varieties of counter we will use. You guys are clear with it, right? Hello. If you are having any doubt, you can ask. Hello.
Like if we are using only one LED,
Yeah.
why like
No. Come again. If you are using only. No,
if we are
actually, I
using only
used. Yeah, using only one. Just I'm showing you for you guys. You can use the 7-segment driver one and connect only one LED. I just done so that you can see how you should connect this thing. Okay, I will show you the use of this two LED in the next Johnson counter. Okay, until then, wait.
yes.
Besides that, you are okay with the counter, right?
Yes.
It looks like a ring. The value goes to this. See the movement of one. The one goes to this after this, and coming again. It looks like a ring, right? So we call it as a ring counter. Okay, I'm moving on to the Johnson counter. Okay, Johnson counter, as you can clearly see, Johnson counter, it's same as ring counter. See, D Q is connected to next D, and similarly, but there is one small correction. At the last flip flop, we are not connecting the Q2 directly to this D. Instead, we are connecting the complement of QR to D. This is how truth table, a state table of a Johnson counter looks like. See, 1000, and after this state, it goes to 1100. Similarly, after some 1, 2, 3, 4, 5, 6, 7, 8, after some 8 iteration, it goes back to our number 1000. Goes back to this. Johnson counter is also known as twisted ring counter. Why? Because uh, looks like exactly like the ring counter, except the last part, right? Last part we twisted like by connecting the complement instead of the normal pin, so that it's known as twisted ring counter. Similarly, I already built the Johnson counter for you guys to see. See, this is how a Johnson counter will look. Okay, wait. Hmm. Can you guys can see the Johnson counter? 00, 08, 12, 14, 15, 07. It's like it's not exactly counting in an ascending or descending order. It's counting in an random order. That is very special to the Johnson counter. Now you can see that both LEDs are lighting up, right, for 14, 15 and all. Now can you see the use of 7 segment driver too? Hello?
Yeah.
Yeah, okay. Make sure that you connect the every pins properly without making any connection with other wires. If you make any connection, like if you mistakenly connected any of the other 2 wires, like it will show you error. Like in this case, if I connect mistakenly connected these 2 wires, it will become some red value and show error. So you should not do such kind of things. Should be very careful while connecting this. That's all. You guys understood how a Johnson counter looks like, right? How it works. With a slight modification to the ring counter we seen earlier. Like you can build Johnson counter and ring counter from scratch using that state diagrams, tables, uh, just by providing the exact value, exact path of the movement. Like in the slide, I have given the truth table for the Johnson and ring counter. From this also, you can like in this case, we have built using a D flip flop. It is possible to build also using T flip flops. You guys, if you guys have time, you can try it out by using T flip flops instead of D. Just add use excitation table of T. Include TA, TB, TC, DD, TD, and make an and make it. So Johnson counter, okay, right? If you have any doubt, you can ask, or any clarification you want, you can ask.
It is clear.
Okay, if it's clear, okay, then thank you guys for attending this session. I guess it's very like in one session, it's very difficult to like observe all concepts and everything we have told. But you've done great job in attending and learning things.